Hello, everyone. Welcome to the session. I hope you're enjoying Summit so far and everything going smoothly for you. I would like you to welcome our new speaker, Anish Lakapragada from Lynbrook High School and Stanford University, who will talk about accelerating the pace of autism diagnosis with machine learning models. Please welcome.
Hello? Okay, wow. Thank you guys so much for coming. I honestly did not expect so many people to come. Hope you guys are having a great time at Databricks. So my name is Anish. I'll be talking today about my research on using machine learning models to aid in autism diagnosis, and specifically with an emphasis on when you have limited data, how do you get a good classification? So just a little bit about me beforehand, a little more background. So I'm a rising junior at Lynbrook High School. Lynbrook High School is a public high school in San Jose, which is 2 hours away. I also love to code, and favorite subreddit, best subreddit is r/programmerhumor. Go in there a lot. And most importantly, I'm also a researcher at the Wall Lab, which is a lab at the Stanford School of Medicine. And their lab focuses a lot on autism diagnosis, specifically with AI. And so the research that I'm presenting is the research that I did last year, and now it's published. So yeah. So here's our agenda just for a quick rundown. So first I'll be going over the problem, and then I'll talk about the workflow of ML, first collecting data, then designing the model, then training it, and then the evaluation process I used, and then how I got the results. Then I'll go through a quick demo with a website that I made, and then we'll have the Q&A session. If you have any questions, feel free to ask, but just please hold them till the very end, because I allocated 5 to 10 minutes for a Q&A session, so that would be very much appreciated. Thanks. Okay, maybe I'll give I'll wait a few minutes and then. Okay, so now I'll go over the problem that I was trying to solve, so a problem statement. So basically autism, this is well explored. Autism diagnoses today, they take too long. So scientists have concluded that autism can be accurately detected in children at 24 months, that's 2 years of age, but oftentimes families will have to wait several months in today's healthcare system, or even a few years, so age 4.5, before they get an actual autism diagnosis. So that's a gap of 2 to 4 in the child's age and growth and development. And it may not seem like a lot, they're both pretty young ages, but the unfortunate thing is that scientists have also concluded that 2 to 4 years old is the ideal time for children with autism to go through early intervention, which can dramatically help their life outcomes and clinical outcomes. And because autism diagnoses are taking too long, it's eating up that time for early intervention, and families aren't getting the best care that they could get. So when you're trying to test if a child has autism, among other things, one of the relevant indicators is repetitive self-stimulatory motion and behavior. So these include hand flapping, which I focus on, head banging, stimming, spinning, anything that's repetitive and self-induced. So one approach to tackle these specific behavioral indicators that has been explored in the literature is using on-body devices. So what this is you use an accelerometer or a gyrometer on a watch and put that to a child and detect whether or not they're doing any of these behaviors. But unfortunately, people have found that in rural areas today, families may have to wait very long or may not even get an autism diagnosis. And because these on-body devices require specialized resources, unfortunately, it may be pretty inaccessible to those in rural areas, and will keep on perpetuating the problem that they're not getting their diagnosis as they should. So my idea was, can we use machine learning basically to aid in this process by detecting one of these behavioral indicators? So machine learning has been explored, but I just wanted to try it on hand flapping because I hadn't seen anything too much in the literature, especially using the approaches that I'll talk about soon. So a quick summary of the research is that I developed novel machine learning models and methods for classifying hand flapping, which is a key indicator of autism. And I'm biased, but I feel this demonstrated that ML is definitely feasible for this area, especially for explainable diagnoses. The research, the paper that I wrote for this research, is now published in JIM or Biomedical Engineering. And if these slides are available, here's the preprint on archive if you ever want to look at it. So, okay, so we just went over the problem statements. Now we're ready to move forward with the actual data collection. So to formulate like the problem that I'm trying to solve in machine learning tasks to make it more clear, it's basically binary classification of whether or not a video has hand flapping or not. And so accordingly, we need data of like videos with hand flapping and without hand flapping. So up to date, the only, we wanted to stick with publicly available data sets. Like our lab said, like we didn't want to record children with autism, like hand flapping or not, because then we'd have to go through like institutional review board and privacy and like whatever other laws. So we chose to stick to with only publicly available data sets, and the only publicly available data set that we could find at that time was Self-Stimulatory Behavior Dataset, or SSBD, and it contains like videos of hand flapping, head banging, and other self-stimulatory behavior. And so basically what SSBD is in a nutshell is it's a folder of like a bunch of XML files, and each of the XML files states, here's the link to a YouTube video where like hand flapping, head banging is displayed, and then it also states some other important information. So for example, in the figure on the image over there, so we would download all of the videos, and then what SSBD would say would basically say something like from the 0 to the 8th second, there's hand flapping, and then like let's say from like the 15th to the 25th second, there's hand flapping. So it'd give the time segments on when there are hand flapping or whatever behaviors in the video. So the way that we use this for our purposes is we basically just we downloaded all the videos, and then like if the 0 to 8 second was annotated with hand flapping, we took that start and end point and cut the video and put it into its own like separate hand flapping like positive category or like pile. And then for the negative or like control videos, because we also needed that to train the model, in between segments with hand flapping, so like from the 0 to 8 second there's hand flapping, and from the 15th to 20th second there's hand flapping, so the 8 to 15 second does not have hand flapping. We would cut that segment out and then use it for like videos without hand flapping. And so to make what SSBD is just a little more clear, here's some frames of the videos. The faces are blurred for confidentiality, but you can see basically that it's mostly toddlers, which is ideal because a model like this would be used of people like who are these similar ages. And so we collected the videos, we sorted them into like the control and positive. But unfortunately, a lot of these videos were shaky because like they are, after all, YouTube videos recorded on a phone. So we cut them out if they had excessive motion and they would just hurt the model performance. And so then at the end of the day, we were left with 50 videos of hand flapping and 50 videos without hand flapping. So now we've gotten the data part out of the way. It's not a lot of data, but it's better than the original 25 videos we started out. It's now 100. So now we're ready to design our model. So one of the models that was like really integral in our entire process was a long short-term memory network, or LSTM. Basically what an LSTM is, in just simple terms, is it's a time series based model, and at each time it's taking in an input, which is like in the image it's like the X's at the bottom, and it's also taking in an internal state representation, which is like the arrows that are propagated through the green like cells. So at each time step it takes an input, and it takes the internal state representation from the past time step, and then like learning through the weights and whatever, it outputs a prediction. So at a very high level, you could think that our research was or like our model was basically, because videos are a sequence of images, so that's why like this sequential model is relevant here. So we pass in each, we didn't actually do this, but you can think of it as a high level as like passing in each image at each time step, and then the final output is a prediction on whether or not there is or there is not hand flapping in the video. Now, the reason on why we didn't like just blankly put each image into the LSTM at each time step is because images are actually very huge, as a lot of you guys probably know. So like a simple image that's like 150 pixels by 150 pixels, that would actually be 3 matrices, each of which is 150 by 150, 3 for like 1 for red, 1 for green, 1 for blue. And so that would be in the order of like 10 to the power of 6 like floats, or like numbers basically. So you could just theoretically squish them into like a flat one-dimensional vector list of numbers and then feed it into the LSTM at each time step. But the problem with that there's no actual learned meaning or anything like that. It would be way too random, and also it'd just be inefficient. So the creativity or like innovation sort of part of our research came in with the fact that we needed to take the images and use some sort of feature extractor to boil them down to a very condensed vector representation for each sample. So our first approach with this was MediaPipe. MediaPipe is Google's framework for pose estimation and landmark detection. Other of its counterparts like OpenPose. Just by a quick show of hands, I'm interested. Have any of you guys heard of MediaPipe? Because I know a lot of people who say they have heard of it. Okay. A lot of people say they have heard of it, and a lot of people say they haven't heard of it. Okay, so that's good, just good to know. So basically, yeah, MediaPipe has a ton of models, but because we're dealing with like hand flapping, the only model that's actually relevant in our case is the hand detection model. And the way that we utilized MediaPipe was basically for every single frame in the image, what we would do is we would pass it to MediaPipe. MediaPipe would then detect, are there any first of all, are there any hands visible in the image? Like the lower right, the lower right figure. So like those are all hands, right? So then MediaPipe would detect, okay, there are hands visible in the image. And then it would find the X and Y and Z coordinates for each of the 21 landmarks on the hand. Landmarks, so like there's another figure there. Landmarks are basically just important points on like a hand. So for example, it's like the base of the hands, the fingertips, these are all relevant landmarks. And so what it would do is it would like evaluate the X and Y, Z coordinates for each of these landmarks with its own machine learning model that's very heavily optimized. So like imagine if this is an image over here, like this is an imaginary image. If my hand is over here and it gets like closer to the edge of the image, then the X coordinate will be less. So like X is the horizontal dimension. Y is the up and down dimension, like how high is the landmark. And Z is the depth dimension, or like distance from the camera, basically, all on a scale of 0 to 1. And so basically what we would do is we would pass in each image to MediaPipe. We would get in the X and Y and Z coordinates for each of these 21 landmarks, and then we would concatenate them into one vector. It's obviously going to be a lot smaller than like 100,000 numbers. And then we'd feed it into the LSTM network at each time step. A little more intuition on why we actually chose this idea was, of course, we wanted to boil down the image to a smaller size that would be more compact, but we were also hoping that the model would learn like the back and forth motion. So for example, in hand flapping, like a hand is going up and down, so the Y, we thought like the Y coordinates would be going in like a sort of sine pattern. Similarly, X could be going back and forth. So that was just our general intuition on why we chose this approach. We were also curious to see how it would go because this had actually never been done before to detect, like this was never an approach that was done before in the literature to detect hand flapping. So just a quick sketch, you take each of the frames of the video, put them through MediaPipe, get like that feature vector, and then pass it through the LSTM and get a prediction. We did some variants of this approach. So the idea that I was just talking about where you take like the X and the Y and the Z and then you merge them and pass them into the LSTM at each time step. We called that the all landmarks approach because they're using all 21 landmarks detected by MediaPipe. Another approach that we tried out was 6 landmarks. Our concern was basically like a given hand pose like this, not all the landmarks would be visible, so we were just wondering if it would be better if we didn't use all the landmarks, even though we could. So the 6 landmark approach only uses the fingertips, so like it only uses the landmarks that are located on the fingertips, which are the 0th, 4th, 8th, 12th, 16th, and 20th on that figure. So then, yeah, we would take them, those landmarks specifically, concatenate them, their XYZ coordinates, and pass them in. There's also the mean landmark approach, which was taking it one step further by only using one position of the hand. And basically what that did was it would calculate all of the XYZ coordinates for all the 21 landmarks, and then would merge them, like take an average, so X average, Y average, Z average, and then pass that in to the model. And we would do this for both hands, by the way. And then there's also the single landmark approach where we wanted to benchmark like the mean landmark. Would it just be better just to plain and simple just use the 0th landmark or the base of the hand and track that over time? So these were our 4 ideas, using all of the landmarks, only using the fingertips, using an average of them, and only using the base of the hand one. This was a pretty unconventional, like this MediaPipe thing was pretty unconventional, so we wanted to benchmark it against something that was more conventional. So for our second approach, we chose something that was a little more well done in this area. And basically what it was is you take, for each frame of an image, pass that image through MobileNet's, specifically version 2, its convolutional layers, and then get the 1,000th length vector and then feed that into the LSTM at each time step. Note that the 1,000th vector is like the penultimate vector in the diagram there. It's not like the class predictions, it's the one before it. And so we would then just pass that into the LSTM. Two things to note is that basically we used a MobileNet V2's convolutional weights pre-trained on ImageNet, and for like to speed up training and like not take as much computational resources. We also made it where the like during backpropagation, if you guys are familiar, the model or like the loss could not update, the gradients could not update MobileNet V2's convolutional layer. So we basically just froze them during training. So this was our second approach. We wanted to benchmark it against the first approach. Okay, so now before results, I just want to go over real quickly our evaluation technique. One thing that we noticed was we would run, like for MediaPipe, we would run it. It would run very fast because it's very compact, could like fit on a CPU. And like we would get different accuracies, wildly different accuracies per each run. And so because of that, we couldn't be too confident in our results basically because we were only dealing with 100 videos. And so we needed a way to figure out like how can we be confident in our results despite of the fact that we don't have a lot of data. So one approach that's usually used to do this is cross-validation. In particular, we use 5-fold cross-validation, which put simply is we took our 100 videos, we put it into like 5 buckets, so 20 videos into each of the buckets. And then in each iteration, like in the image, we first trained on like the first 4 buckets. Then we first trained on the first 4 buckets, and then we used the last one for testing. And then in the second iteration, we trained on a different set of 4 and tested it on a different one, on like a different bucket, basically, and so on and so forth. So it's essentially like you're creating 5 different training and testing splits. So we use this, and then we also noticed that it still did not average out the randomness that comes with just having not like limited amounts of data. Our hypothesis on why this was, like why cross-validation wasn't leading to stable, confident results, was because of the fact that when you have a lot of, like, very little data, let's say there's a video, we'll call it like video A, what could happen is that video A has some information that the model can learn that no other video does. And so if that video A appears in the test set instead of the training set, then it's going to be very bad because the model will not learn that information that it needs from video A. So that's our hypothesis on why like the specific shuffle of the videos in each bucket mattered a lot. And because it was mattering a lot and we couldn't, it was not leading to stable metrics, we needed another way or a more confident way. And that turned out just to be running 5-fold cross-validation 100 times. So basically what that meant is that we created 100 different data sets of each of the 5 folds, or in other words, just 500 different training and testing splits of the videos. And we evaluated it for like the all landmarks approach, the 6 landmarks approach, the 1 landmark, the mean landmark, and the MobileNet approach. And it led to much stabler results, and yeah, it was needed, this was what we needed to do to get a confident result. Okay, so now for our results finally. Metrics, real quick. So we used tracked the ROC curve, which is the receiver operating characteristics curve. You basically need, it's like these are all examples of what they could look like. Ideally, the area under the ROC curve or like integral will be as high as possible. We also track precision, recall, and F1 throughout training and testing. So now for the results, I'll first go over MediaPipe, which was, just to recap, it's like the hand coordinates one. So we got in the high 69 to 70% accuracy. One thing that was interesting with MediaPipe was that it actually had 100,000, no, not 100, a million more, almost a million more trainable parameters compared to MobileNet V2, yet it still could not, despite having more parameters, overfit to 100% accuracy. We also noticed that with MediaPipe, there was like a clear hierarchy on which of the variants worked best. So using the 6 landmarks and the all landmarks approach, their results were comparable, but the single landmark approach, like the mean landmark and 1 landmark, did dramatically worse. For the second approach, the conventional MobileNet V2, it did a lot better. It hovered in the 85% accuracy range. It had 1 million less parameters, but it was able to overfit to 100% accuracy on like the training set. And it was overall just a much more smooth and accurate model. One of the hypotheses on why it was able to overfit that well, despite having less trainable parameters, is just because the ImageNet representation of the MobileNet representation after its weights have been pre-trained on ImageNet was just that refined and unbeatable, basically. So here are some more comparisons. You can see that the 6 landmarks, which performed the best, was like it had a lot more jagged ROC curve, whereas MobileNet was a lot more smooth, and its results were also slightly better. So yeah. Okay. So next, just before we go over like the demo, a little bit about the a recap of what contributions we made. So we were able, we started off with 25 videos, and we were able to achieve like 85% substantial performance without typical ML data amounts. The model was able to deliver predictions in like less than 10 seconds, and I think that also shows that there's a pretty good potential for a remote and accessible diagnosis using machine learning, basically. So now This is the GitHub repository. Please star it if you get a chance. But I'd just like to quickly go over the code that I used to write how I built it in TensorFlow. So first load MobileNet V2 pre-trained on ImageNet from Keras, and then set it all to false, and then attach an LSTM for each time step, and then an output. We chose sigmoid because it's binary classification. And then one last thing. So I created like a small little website demo to upload videos. It'll take like roughly 15 seconds to load, because right now it's just reading in all of the weights, because I trained it already. But yeah, so I'll just wait for a few. Yeah. What? Oh, yeah. Oh, okay. I see. Ask. Oh, shoot, sorry. But basically what I was just showing was very simple. It's just like how I loaded in the model. This is the crucial part where I load in MobileNet using Keras applications and freeze all of its weights and make them not trainable. And right now I'm running a demo. Okay, phew. So now you just upload a video, basically. I wanted to deploy it, so this is me in my hotel room. Yeah, not to offend anybody who actually has autism. One thing to note, though, is that the model will not perform as well on like a grown man like me hand flapping, because it was trained on toddlers. So yeah, predict. I wanted to host it, but like TensorFlow takes, so this is correct, but TensorFlow takes a lot of space for any free store service. So yeah, hand flapping with a confidence is 0.73. Let me also try another. Let's see if it works. So this is me drinking from the, no hand flapping with a confidence of 0.79, 5.16 seconds. Okay, so yeah, that's basically it. Thank you guys so much for coming. Please don't. Yeah, okay, now for the Q&A. Please leave a good review, by the way. All right, now for the Q&A session. Sure.
Did anything surprise you in terms of the subtlety of the hand motions that your model was able to pick up? Were there things that were labeled as hand flapping that you wouldn't pick up if you were just watching them? If you were watching the video yourself, would you see something as not hand flapping and your model picked it up, maybe more subtle motions as hand flapping?
Maybe more subtle. Oh, I see.
I'm just curious if you had any surprising results in
that way. I don't think I did, because I checked through all of the videos to make sure that like they actually were hand flapping, because there's also a possibility that they were not, and that SSBD, or like the creators of SSBD mislabeled that this time segment contained hand flapping. But yeah, I did not notice. Any other questions?
Thank you.
Do you have any plans to either extend the data set or to use it, or any practical way of using it right now? I know you showed potentially using it for remote diagnoses and things. Is there anything, any discussion further?
One thing I think would be possible is like, I'm working with the lab right now to add like another so one person's already working on like a head banging model, because that's like another behavioral indicator. So another one would be like spinning or emotion. And then one thing that I was actually trying out was like combining them all, like I'm currently working on it, but combining them all to make like a meta model. So like an ensemble, so like one predicting hand flapping, which is this, one predicting head banging, one predicting maybe emotion, because that's another area that's like can be applied to ML and that people with autism struggle with. So yeah, like creating an ensemble basically, I think that would be a good future plan.
Hi, I was just wondering if you had any future considerations for high-functioning children with more subtle behaviours.
Wait, sorry, I didn't get the second part. What you wanted to say again?
Just if you had any like future considerations for children that have more subtle behaviours.
That have more subtle behavior. I would definitely like do this project or like any other project for anything else if there's data in the space though. So right now what I'm, like another thing that I'm looking at is like, are there more data sets? Because it's like, a lot of people note that there's not, and like SSBD was the only at the time publication that I knew of that was only available. So a lot of labs, like what they do in papers is they collect like videos of those people with autism, and like those are private. So I guess I'd have to have more data to do any more classification, I guess, yeah. But I would love to if there was more data in the space. Any other questions? Yes.
Just wanted to know about, you directly put it into ResNet, but then what about things like object detection? So suppose you're talking about hands and head, then do you do some pre-processing around there?
No, other than like splitting the videos to extract and like
Images.
also that's like mostly the pre-processing that I did.
Okay. Yeah, I mean, I'm just thinking about in a diverse set, you might not be able to detect hand. There would be other things which could be of the similar shapes and stuff like that, but then I guess your data set is not that big right now, so.
Yeah, that's unfortunate. Yeah, that's a good point.
Thanks.
Hi, did you have any visualization process to see why the model made the decision? Like, did you have a heat map of the things the model looked into the frames?
I was unsure. How would a heat map? That would be interesting to try to create. But no, we did not. But now that I think of it, that would be nice to try like seeing a heat map for each frame in the video and seeing how that led to the prediction. But no, I have not. Sorry.
I just asked if there was if he had a threshold against, he ran a benchmark, was there a threshold that made him decide this is spectrum behavior versus some random movements that are not spectrum behavior?
We were predicting hand flapping in hopes for, like we were not directly predicting like autism, but our threshold was, we set it at 0.5. I guess that's sort of what the ROC curve is trying to, like, this curve I think is somewhat related to like, at various thresholds, what is the accuracy sort of.
Any other questions, guys and girls?
Once again, okay.
Given that you had so few videos to work with, and then you ended up slicing both positive and negative examples from each video, did you worry at all that those would pick up on things just because the videos were so similar?
Just because, I mean, it's working on the same data set, so like if there was a different data set for positive videos and a different data set for negative videos, then there could definitely be data set bias that like it would learn that it's from this data set, so it's probably negative, but because it was all from the same data set, I'm a little bit unsure on how there would be data set, because it's acting on both sides, right? For like the specific attributes that are like really random of the data set, like that's on the negative and positive side. So I don't see how the model could leverage that. I don't see how the model could leverage that in detecting whether, in its classification on whether or not there is or is not hand flapping.
Cool.
Okay, so is your model classifying whether this this behavior is hand flapping or not, or is it actually diagnosing autism?
It's classifying whether or not it's hand flapping or not, because SSBD has no labels for autism and no autism, so like it would we couldn't make that prediction basically.
Okay, are you planning to expand this research into the actual diagnosis part?
Yeah, our lab has like a small data set for the, like where it's logged videos of people with autism and without autism. So I'm thinking maybe just try this approach, and instead of predicting hand flapping or not hand flapping, just directly predict autism.
Okay, and also the follow-up question is, what do you think is like the factors contributing to like accuracy of like 85%? Like if you want to increase it to like over 90, what would you need to, maybe like it's about data or the model?
I think the most important step is, like, we can optimize the model, but I think the most important step I would first take is getting more data.
So you think the number of data is like the major factor?
I think the right now, like if I wanted to improve the model, the number of data would be the the most important thing.
Okay, thank you.
Thank you very much. Please give a huge round of applause to our speaker. If you have any further questions, our speakers will be around, so you can just catch them in a venue. And please don't forget to rate the session afterwards. Thank you.
Thank you guys so much for coming. That means a lot, actually. Yeah. I did not expect so many people to come.